I guess it's just the mystery of life that really attracts me. How is it that we came to be? And in particular, and this is still like a huge fascination, like how is it that something that started as a unicellular life form developed all the way to where we are sitting here, connected across a huge distance, speaking to each other about, you know, life in the universe. Yeah, so I think that's what biology is to me, and I could spend more than a single lifetime researching this. Yeah.
What's up, everybody? From Nautilus, I'm Brian Gallagher, and you're watching Behind the Scenes. Today I'm speaking with Elena Kazamia. Elena is a scientist and writer. She did her PhD at Cambridge University on synthetic ecology and is now a research scientist at Viridos, a company that seeks to harness photosynthesis with microalgae to create alternatives to fossil fuels. Her recent story in Nautilus was The Universal Clock of Aging. Elena, thanks for joining us.
Thanks for having me, Brian.
So, to start off, would you mind summarizing your intellectual background and academic background a little bit?
Sure, yeah. I'm originally from Greece, but all of my studies were in the UK, so I moved there when I was 18. I did my undergraduate at Cambridge on biology, fundamental biology, really. The course is called Natural Sciences. It includes all aspects of biology. And then after that, I did a quick master's in conservation. I thought I wanted to be a park manager. Changed my mind, went back to do a bit more science, and I did a PhD on algal science, studying like ways in which we can harness the power of algae to create sustainable alternatives to fuel. That was a while ago. After that, I had about 8 years of postdocing around the globe until I finally found a home here perched on the west coast of the United States, where I now work for Viridos, kind of going back to my roots and working a little bit on algae again for biofuel production, like you said.
Nice. What drew you to biology in the first place?
Um, Actually, it's a funny question. I found recently like some notes that I had from when I was 12. And I didn't realize, but I already back then wanted to be a biologist. Um, I guess it's just the mystery of life that really attracts me. How is it that we came to be? And in particular, and this is still like a huge fascination, like how is it that something that started as a unicellular life form developed all the way to where we are sitting here, connected across a huge distance, speaking to each other about, you know, life in the universe. Yeah, so I think that's what biology is to me, and I could spend more than a single lifetime researching this. Yeah.
And what drew you along the path to studying algae and synthetic ecology and the potential for that uh, to use as biofuel?
Yeah, good question. I don't think anybody dreams of becoming an algal scientist. I don't think I knew what algae were until I was really, truly like knee deep in researching them. I think because of this interlude in my life where I cared deeply, and I still do, about sort of the environment and conservation, the opportunity arose to think about sustainable energy. So it started with sustainable energy, and then kind of the algae came back into that. Um, it was a time where I kind of left behind these like more philosophical thoughts on cells and so on, although I came back to that. So I wanted to do something useful with my PhD. I wanted to work on sustainable energy. Algae was the hot thing. That was around 2008. It still is today. Things kind of come around in circles. So yes, I started working on sustainability, and algal biofuels were made sense. But then along the way, I realized that just as far as cells go, algae are actually really exciting. They're a lot more exciting to me now than most other cell types. There's just so many different kinds. They have fascinating biologies that are so disparate compared to, like, if you study human cells, most of them are actually pretty similar, even though we have cells like a brain cell and a heart cell. But if you study two algal cells, they can be just worlds apart. So yeah, I kind of fell in love with algae, but it it took me a while to really get there. And so then, yes, for the next 8 years, I really started thinking more about, well, those cells live alone in the ocean, but do they really? Like, does anything really live alone? And what kind of interactions algal cells can engage in the ocean? And that's where the idea of synthetic ecology comes along. So it's trying to understand if there are any kind of ecological symbiotic interactions between algal cells, can we harness that to produce a more stable ecosystem even in an engineering context, like for the production of biofuels? And the reasoning behind that is it's always better, I think, to mimic what's natural. And in nature, nothing lives alone. So when it comes to practices like in agriculture, we grow things on their own. And that can be quite frustrating, like things get infected or like pests come along, whereas like communities that are more complex are more stable. So that's what synthetic ecology is all about.
That's very cool. One more question before we get to your story, because I'm curious. Where do you see biofuels and maybe biofuels coming particularly from algae in the future landscape of renewable energy and alongside other ways we're generating electricity, like through solar power and wind?
Yeah, that's a great question. I think it depends, which side of the bed I wake up on, like as an optimist or as a pessimist. Um, Hopefully, I mean, there is certainly a place for algal biofuels in this landscape, and a pretty important one. They can very easily replace liquid fuels, which not many things can. Things like aircraft will always, at least in the foreseeable future, I don't know, maybe we'll come up with a different way of flying around. But for now, we're kind of stuck with a combustion engine that relies on liquid fuel. And algal biodiesel can replace that, can replace the fossil diesel component of that. Um, but overall, I think, it's when there's a frustration there too, and that a lot of great ideas need backing, they need funding, they need political clout behind them, they need support. And I did my PhD in 2008, and everybody thought that was the future. And here we are again, thinking it's the future. And I think it only becomes a reality if enough people want to make it a reality. Economics obviously comes into play too. But no, I think the potential is there. I just really hope to see it in the pipeline soon.
All right, once again, your recent story in Nautilus was the universal clock of aging. Would you mind giving us a brief summary of that story for our viewers who haven't read it yet?
Yeah, absolutely. It's a great story. I hope people read it. It's mainly based on the work of Stephen Horvath, who's a professor, used to be a professor at UCLA, but he's actually moved on from academia very recently. But his work discovered this universal clock in cells that can effectively measure time. So it allows us to age a particular tissue. And the cool thing about this is that the unexpected result is that there's a single formula based on certain DNA signatures in cells that can reliably tell us how old that tissue is. And it works across every tissue in a body, but also across all mammals, or at least more than 150 mammals that were studied. And that's really surprising. I think it's very rare to have findings in biology that hold across cell types, across like a variety of life. I think it speaks to something very fundamental, very core in biology, and the result was unexpected. And it tells us, I think, that there must be some sort of program to aging, or at least that's what the field believes now. And that's also quite remarkable. We don't expect, if you think of a body, there's a lot of cells that are collaborating, right? Like your brain cells have to be collaborating with the blood cells in your body so that you stay alive. But a brain cell lives a lot longer than a red blood cell. So it's kind of weird that they measure time at the same rate, though. So, and it's not clear why they do it. It's not clear exactly how they do it, but it's pretty neat that they do it. Yeah.
So in the piece, you describe aging as a kind of coding error.
hmm
Does that imply that the aging process wasn't sort of a positive adaptation, but just sort of incidental result of other things that were going on?
I think that's definitely how Horvath and some of his colleagues see it for sure. Mainly because, there's this clock and we know that certain things are older than others, and there is sort of signatures in the DNA that we can relate that back to. But mechanistically, trying to understand why that's the case is trickier. And one of the things that is now clear is that part of that clock machinery relies or kind of tells the story of development. So a single cell starts off, as a stem cell, completely undifferentiated, can become anything, and then gradually it chooses a path and it ages along that path. To develop is to age, and so that part is really now more and more clear biologically speaking, like the mechanism is clear and that part of the clock is clear. But then the second half of that is that there's kind of like this runaway development, I guess. So cells go from being young and pluripotent, they can become anything. Then they finally choose a path, they develop, you have a mature cell, you have an adult body, but then the development kind of continues seemingly unnecessarily. And yeah, so that's what Horvath and his colleagues call this coding error, that there's no real need for it. And yeah, but I would say that having spoken to them, I think there's still a lot of kind of debate around this. Is it intentional or unintentional? Horvath certainly sees it as an unintentional consequence, but he's just on one side of that argument. There are others who believe that there is an intentional kind of like death program, that we are programmed to age further and to then die. He doesn't believe in that.
So, what is important about that distinction is that, at least in some minds, it could matter for our ability to stop aging or slow aging, right? Because if aging is something that was selected for in our evolutionary history, that could imply that it would be harder to get rid of or reverse. Is that right?
Yeah, absolutely. I think, if we're saying we're programmed to die, then it's difficult, then you're in for a hand combat against evolution, right? And often we lose that one. But if it's just kind of this unintentional thing that happens, doesn't bring any benefit, it's not really selected for, then that gives you more space to try to reverse it, and or at least to stop it, to kind of briefly pause it so that we can hover around like youthfulness for just a little bit longer, right?
Do we know anything about how this formula that Horvath has derived can inform approaches to stop or reverse aging?
I think that's certainly something that they're hoping to really get down to in the future. There are certain indications already how that might work. So one of the colleagues of Horvath, who I spoke to, Vadim Gladyshev, he's a professor at Harvard Medical School, and the way he explained it to me is that there are certain wrinkles, I guess, in the DNA that are kind of there, but they're not causative. So let's say we studied aging, the way he explained it to me is he said, okay, let's think about all the hallmarks of aging that are visible to us. So people start using walking sticks, Zimmer frames, wearing glasses, right? Those are all things that happen as we age. And so if we were measuring that, okay, how many people with, reading glasses there are, like, and trying to date them according to that trait, we would we would not necessarily learn something about aging, because you take the glasses away and the people are still old, right? That's just something that comes along in the bandwagon of aging. But if we can understand why people are wearing the glasses, then you're really uncovering like the real cause of the aging or the phenomenon that you're seeing. So in this molecular clock that Horvath has developed, we know there are very specific regions of DNA that are altered as we age. We don't know if some of those are just kind of random glasses like modifications, or if we're looking at something that's deeply causative. And if it is deeply causative, then we can try to understand the molecular mechanism behind that and reverse it. So there are some things that are very exciting in that. The one particular aspect of DNA that's very kind of, it's a little bit technical, but these are the Yamanaka factors that people are looking at. We know that if we take away those factors, we can actually revert cells all the way back to like a nascent state, but that's like a really brute force approach. So you go from an adult cell all the way to an embryonic cell. And that's too much, right? We don't want to do that. But that's already, that's promising in the sense that we're getting there, that it's possible, right? Like that the mechanisms are there. We don't know, we don't have like the finesse on them yet, but at least we scientists have shown that it is possible to revert cells back to an earlier state. Now, I don't know. I think in terms of industry, how close we are to that, the feeling I got was that we're quite far, but nobody really wants to say how far, because you don't want to take the potential away, right, from research in that area. Yeah.
What was your impetus or the inspiration for writing about the biological clock now?
Well, Nautilus magazine is probably the best answer. I'm a big fan of the writing. I actually wanted to write about death in cells. Why do some cells die? It's not really obvious that that has to happen. A lot of cells choose to commit suicide even though they're free living. And it was through a discussion with one of your colleagues, Kevin Berger, that we started sort of having a conversation about what would an interesting piece be. We talked about cell death, and then decided that cell aging is obviously part of that process, right? Before death, you age. And so for a first piece, we landed on this story, and I'm really glad that I got to cover it, because I read some fascinating science along the way.
What were some of your first thoughts about how to start writing the story?
Um, well, I guess whenever I write, I like to think about kind of the bigger context. It's the reason I like writing so much. Science is really great fun, but it's also kind of, sometimes it can be a little bit cool. You have to stay rational. There's like a very specific scientific method and approach to doing experiments. I like the more artistic side of things, the philosophy behind things. So why do we think the way we do? Why are we even thinking or researching this? And obviously, aging is something that bothers all of us, even if we don't particularly want to admit so. And so in writing the piece, I started thinking about pieces of literature that cover aging, I guess, and there's many. There's a lot of great work that studies aging, from like the simplest, the Peter Pan phenomenon to, Dorian Gray, of course. And yeah, so that's kind of how I wanted to begin, is to kind of touch on something that's very human in us. Why does it matter to us? And then kind of get more into the nitty-gritty of the fascinating science that has been recently discovered. And like I think the science is interesting both from that perspective, like the human perspective, but also in and of itself. The fact that it is this universal phenomenon that I already talked about earlier.
Can you tell us about any more interesting tidbits or anecdotes or ideas that you had for the piece but didn't end up making it in the story?
Yeah, for sure. One of the things that I didn't get to really read about enough, but that kind of came up, and I wish I had more time to think about, is the idea of the menopause in humans. So there's no particular. It's a little bit paradoxical that along this aging process, that we hit a point where we're reproductively incapable of continuing, right? We can't bear children, but we continue living. If you think of Darwinian evolution, that doesn't necessarily make any sense. You should, if you are out there to propagate, and there's many. I mean, this is a complicated topic, and there's many hypotheses about why there is a menopause in our species, and I'm not exactly sure if it occurs in other primates, for example. I don't believe so. But the aging clock actually can tell us something about how that happens and why that happens. And it's one of the things that Horvath and his colleagues are thinking about. And the goal there potentially would be to expand the reproductive age of people, going forward to, late into their 60s. um, I'm 36. I've just had a baby. I don't know if I'd be capable of having a baby in my 60s. I already feel quite spent energy-wise. But yeah, I mean, it's a fascinating question. It's part of the whole like aging saga, and that was certainly very exciting. The Yamanaka factors too. I didn't really know about. I didn't get to cover that part of the story. And again, like, it seems that there's just four proteins in the cell that can revert it all the way back, if you inactivate them all the way back to its kind of nascent state. I think that's pretty astounding, that it's a simple mechanism. Yeah, so I didn't get to cover that in the piece.
Yeah, it's a fascinating area. I believe we've had a piece on that topic by the evolutionary psychologist David Barish called "What Good Is Grandma?" It's about
Okay.
why evolution would have selected for menopause,
Mhm.
given the benefits that grandmothers could offer to their offspring and grandchildren in providing sort of social support and food gathering and stuff like that. They could um, help further their reproductive success, not by necessarily reproducing, but by kind of ensuring the survival of their descendants. I think hopefully I did some justice to that argument, but yeah, it's really
Yeah,
cool.
for sure. That I think that is the dominant hypothesis. Yeah, is the
Yeah.
grandmother support. Yeah. Oh, and just one other thing that I didn't get to cover now that I think about it, that was really cool. Is when I spoke to Horvath about aging, one of the things he said about kind of anti-aging therapies is that the clock for humans is actually ticking really slowly. So,
Mm.
and in his mind, like what he's trying to say is that we're already kind of selected to age pretty slowly. And if you look across all mammals, there are species that age very slowly, like the naked mole rat, certain types of whales, and we're out there with them. So so in a way, and I don't think he didn't really commit himself to saying that, but I think the point is that if you try to rewind that clock, you have to be careful and quite dexterous at doing it properly, because we're already aging pretty slowly compared to other things. So it's not necessarily clear how much more we can gain. Yeah.
Mm. What are you working on at the moment? Any other stories or anything interesting you can tell us about the work you're doing professionally for Viridos?
Yeah, so I mean, I'm on maternity leave from Viridos, which I'm actually really
Um,
enjoying. It gives me more time to write. I have I've written a book and I'm writing a second. The first book is not out yet, so it's still kind of in discussion with publishers and agents and so on. But my second book is on the intersection between art and science. And it's a bit of a strange one, not the intersection kind of intellectually, but I'm trying to tell the story of the origin of the cell, but through art movements. It's quite quirky. I'll give you an example. I guess the first chapter is about like the emergence of the cell out of the primordial soup, and I compare that to the work of Kazimir Malevich, who kind of drew these squares emerging out of a background, and I think they're trying to capture the same feeling or moment, I guess, the moment of creation. So there's a lot of parallels in how he does it and how I think cells could have possibly done it too. So that's what I'm working on. I'm also hoping to have more stories in the future out in Nautilus. Again, I think I have possibly a pitch coming together on art and the COVID-19 molecule, not molecule, like viral particle, which would be
Excellent.
exciting.
I love that as
Yeah.
an angle, telling the history of life or the development of life through artistic movements. That's super cool.
Oh, thank you.
Yeah,
Yeah.
I mean,
You
yeah,
might be in a
I don't think I've
minority
ever
there,
heard of
but
anyone. All right,
yeah.
to close out, would you mind telling our viewers where they could find you online? Do you have a website they could visit or social media accounts they can follow?
Sure, yeah. I'm both omnipresent and not really present on the internet. So I have a personal Instagram account. It's dr underscore KAZZIE, Dr. Kazi. It's open to the public, but it doesn't necessarily have a very consistent theme across it. I also have a website, ekazamia.com, and I write a Medium blog so I write a blog on medium.com. So you could find me all across there. And I hope to have a more coherent and consistent internet presence moving forward.
All right, excellent. Well, Elena, appreciate your time very much. It was a fascinating discussion.
It was great talking to you too, Brian. Yeah.